Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from the University of Hong Kong, Utonia, toward one encoder for all point clouds. Imagine a single model that understands every kind of point cloud, from city-scale LiDAR scans to small CAD objects. Today, most 3D models are trained separately for different domains. Utonia asks a simple but powerful question: can one encoder learn a unified representation for all of them? Point clouds are a geometry-first view of the world. Instead of pixels on a grid, we have scattered points representing real 3D surfaces. This makes them powerful for robotics, AR, and autonomous driving. But it also makes learning much harder. Unlike images, point clouds are sparse, irregular, and vary dramatically across sensors and environments. A LiDAR scan of a highway, a room reconstruction, and a CAD model of a chair are all point clouds, but they look completely different to a neural network. They vary in scale, density, and coordinate conventions. Because of this, most existing methods train separate models for each domain. As a result, representations fragment instead of generalizing. Utonia explores a new direction, training a single self-supervised point transformer across many domains simultaneously. The model learns from indoor scans, outdoor LiDAR, object datasets, and even point clouds reconstructed from videos. The idea is simple. If all point clouds represent the same 3D world, we should be able to learn a shared representation. But simply mixing datasets does not work. The authors identify three major problems. First, different datasets operate at different spatial scales. Second, many scene datasets assume gravity alignment, while object datasets do not. And third, input modalities like color and normals are inconsistently available. Without addressing these mismatches, joint training collapses. One key insight is perceptual granularity. In sparse 3D models, grid size defines the spatial unit of interaction. If datasets use different scales, the model learns domain-specific geometry instead of general patterns. Utonia solves this by rescaling coordinates so all point clouds share a comparable spatial granularity during training. The Utonia system builds on the point transformer V3 architecture and introduces several minimal but important improvements. It aligns spatial granularity, integrates rotary positional embeddings, and trains across multiple domains simultaneously. These changes allow the model to learn geometry that transfers across datasets instead of specializing to one. Another challenge is inconsistent modalities. Some point clouds include color and surface normals, others do not. If the model always sees color, it may depend on it too strongly. Utonia introduces causal modality blinding, randomly removing these channels during training. This forces the model to rely on geometry while still benefiting from extra cues when available. Utonia also adapts rotary positional embeddings, commonly used in language models, for 3D point transformers. Applied to aligned coordinates, ROPE gives attention layers a continuous representation of spatial relationships. This makes the model less sensitive to sampling patterns and density differences across domains. The benefit of modality blinding becomes clear when inputs change. When colors or normals are removed, earlier models lose a large amount of performance. Utonia remains far more stable, showing that it learned geometry-centric representations rather than relying on dataset-specific signals. Across standard benchmarks, Utonia performs competitively with or better than previous state-of-the-art methods. Importantly, it achieves this with a single unified encoder, rather than separate models for each domain. That suggests cross-domain training can actually improve representation quality. Interestingly, the benefits go beyond perception. When Utonia features are integrated into vision language models, they improve tasks like 3D visual grounding and question answering. This suggests that strong geometric representations can help higher-level spatial reasoning as well. The unified representation also helps robotics. When used in vision language action policies, Utonia improves manipulation success rates. The model produces coherent features that separate objects from supporting surfaces, even under occlusion. That makes it useful for grasp planning and complex robot interactions. Utonia shows that unified point cloud representation learning is possible by addressing cross-domain mismatches with a few simple ideas: granularity alignment, modality blinding, and ROPE positional encoding. The model learns geometry that transfers across very different datasets. This moves us closer to foundation models for 3D spatial understanding.